Hey guys, my name is Elliot, and today I'm going to talk to you a little bit about pulse code modulation, which is essentially how computers receive and process sound. So before we get into how computers receive and process sound, we should first understand what sound actually is and how us as humans receive and process it. From there, we can look into how computers do it, and then if I have some time, I'll show you some cool things that you can do with JavaScript. So what is sound? Sound at a very high level is essentially just variations in air pressure. So my vocal cords, that speaker over there, they're causing variations in air pressure which are creating waves which your ears capture and your brain perceives as sound. Now humans can hear anywhere from between 20 hertz and 20,000 hertz. And in terms of frequency, a hertz is the number of complete wave completions, basically going up and down, that a wave makes per second. So the wave on the right, the little GIF, gets to a maximum of 5 hertz, which would be inaudible by humans and is a very, very low tone. So I just wanted to get into a couple wave examples to show you how different shapes and how they can literally sound sort of how they look. In oscillator A right here, this is what's called a sine wave. And as you can see, it's very smooth, and when you play it, well, if you didn't play it through those, if you played it through other speakers, it would sound very smooth. On the right is what's called a sawtooth wave, and it's very sharp. And it sounds very sharp when you play it compared to a sine wave with a non-broken speaker. So before we get into digital signals, let's talk about analog signals. So how it used to be. Imagine talking into an old telephone. What's actually happening is your voice is vibrating a metal diaphragm inside of the mouthpiece. This produces current variations, which then produce waves, literally electrical current waves along the wire. The problem, and this produces a waveform. When the person receives it on the other end, their earpiece processes those sound waves and it creates sound. The problem with this is that the wave, similar to throwing a rock or a pebble into a pond, the further you get away from where the rock hit in the pond or where your voice caused the metal diaphragm to vibrate, the wave deteriorates. So we have digital signals. And pulse amplitude modulation is essentially the backbone behind pulse code modulation. And I'm going to talk about hertz a little bit because hertz in this example is going to be how many times per second that we sample a specific audio source. So for example, a phone is a mono audio source, meaning that there is one channel of audio. Essentially, if you were to wear headphones listening to a phone, it would be the exact same audio in your left ear as in your right ear. Those old telephones are processed at 8,000 hertz, meaning that they're sampled 8,000 times per second. You probably wouldn't want to listen to music through a phone because it's going to sound fuzzy and overall crappy. CDs, on the other hand, are stereo signals, meaning that the left channel and the right channel are totally separate audio sources, totally separate waves, totally different waves. The CDs are sampled 44,100 times per second. This is due to what's called the Nyquist-Shannon theorem, which says that you should sample an audio source 2 times the maximum amount of frequency that you're trying to achieve, which in the case for humans is 20,000. CDs would then be 40,000, would then need to be sampled 40,000 times per second. The extra 4,000 is for things like anti-aliasing, which is a whole nother topic. But it just gives a little bit of room to play with the sound without getting into the audible range of humans. Now, pulse amplitude modulation is basically transforming a wave into number values. So as you can see on the right, there are blue dots. And at each one of those, imagine each blue dot being a sliver, a sample sliver. So in the case of a CD, we're doing that 44,000 times per second. We're placing a number value on to essentially this graph that is going to map out the wave. Now, to create an 8-bit depth, we need to be able to represent each one of these numbers with 8 bits. So that is why the graph on the right is between 0 and 255, giving us 256 possible values so that we can represent it in 8 bits. This is essentially pulse code modulation. Pulse code modulation takes those number values with pulse amplitude modulation and converts them into binary, and is then a stream of binary that a computer can understand. And if you were to plot those numbers on a graph, you'd literally see a wave. There's some arguments between 8-bit and 16-bit. 8-bit you get a ton of, or you don't get a ton, you get 256 possible values. With 16-bit you get 65,000 possible values. And as you can imagine, the more possible values that you have, the smoother the numerical representation of the wave would be. The problem is that for a lot of people, it really doesn't matter. So here's an 8-bit sample of size Gangnam Style. Sounds fine. 16-bit. Sounds pretty much, well, it sounds literally the exact same coming out of most speakers, coming out of most headphones. Some people may be able to tell a difference, but the point that I'm trying to make is that it's really not that big of a difference, and 8 bits is plenty. What's interesting is that the Web Audio API actually returns a 32-bit float numbers, which is kind of odd to me, but it gives a lot of possible values for the different points in the wave. Now, when I was researching this, something cool that I discovered was how noise cancellation works. And I sort of knew how it works in that you essentially send a wave that is the exact opposite of one wave, and it should cancel out the other wave. So in terms of Bose headphones, it samples the outside noise and basically switches the phase of that noise to cancel out the wave so that you essentially hear nothing. The interesting thing about phase and noise cancellation is that humans can't hear the difference between phase. They can only discern amplitude. So for my Stackathon, I created an app called Mesh, which essentially meshes 2 different audio sources together. So if we have, I'm going to upload a song or part of a song. So this is what it sounds like totally. This is what it sounds like. But if we mesh the two, it's mathematically, I know exactly what's going to happen, but I just have to do it to show you that if you mesh those 2 waves together, what you get is complete silence. So that's how noise cancellation works. I don't have enough time to go over some cool things that you can do with it, but Mozilla Docs has some great resources. When the API is pretty straightforward, they have good examples, and there's a lot of cool things that you can do with it. So thanks for coming.